data sets. Now, as we said, this is just a review. When variables used in regression are possessed of trends, if they contain trends, whether they are linear, exponential, etc., the problem with variables that possess trends is the spurious regression problem. What is that problem again? It's the phenomenon of finding a relationship between two or more trending variables simply because each one is growing over time, which is not, doesn't mean one variable is causing changes in the other. Now, last time we talked about how to solve the problem of spurious regression. The problem or the method of solving spurious regression the solution comes in two kinds. One kind is just to add a trend term to the set of explanatory variables. So it's as simple as adding another independent variable, which is time. Okay? So you create this artificial variable or data, which is time, which is just numbered chronologically. 1, 2, 3, 4, 5, etc. Okay? Now, we can skip the example. We've talked about this already. I'm just reviewing. Now, let's go to method 2. Even though method 1 is simple, can easily be carried out, it also helps to talk about method number 2. Method number 2 says to detrend all the offending variables. Actually here, I need to recheck this. It's in all variables, whether those that contain trends or and those that don't, or only the ones that contain trends. I need to recheck this. But I would suppose it would only be those that contain trends. So detrend all the variables prior to estimation. Okay. So our first lesson for this afternoon is, what do you mean by detrending? Detrending. So I'd like to give you a metaphor. When you say you debone a fish, you take out the bones of the fish, right? So here we're saying you're detrending the variable. So you remove the trend. Okay, now how do you remove the trend in the variable? So we have two steps here. Actually, it's only step 1, that is the detrending. Regress y, x sub 1, x sub t, all the variables in your regression, separately or individually on time, t, and obtain the residuals. Then, to carry out the regression, regress the residual of y on the residuals of x1, x2, etc., and no need for an intercept. Okay, let me explain. Let me explain. Okay. So, let's see. So you will regress, according to step 1, you will regress your yt on time. Okay, so let's say I have this equation. Okay? I will regress y sub t on time. So I have two constants, alpha 0 and alpha 1. And then alpha 1, the slope, is multiplied to time, and then I have a error term. Okay, now, once you run OLS, so you run OLS on this simple regression model, what will that return to you? What will you get? When you run OLS on this, you'll get an estimate of alpha 0, and you'll get an estimate of alpha 1. Okay? Then, when you substitute it back into the equation, you'll get your, what do you call it? The fitted value. Okay? Right? You get the fitted value. Now, once you get the fitted value, you subtract the fitted value from the actual data y, what will you get? You'll get the residual. So here it's e. So you'll get the residual. Step 1 says regress y, x sub 1, x sub 2, separately or individually on time and obtain the residuals. So this one we do. You do this. We'll get the residuals. Then you do the same thing for x sub 1, x sub 2. So you make also a regression of x sub 1, let's say as a function of time. Then we have error term, let's say b1. So you regress x sub 1 time on time, and then you'll get a residual. So when you do the same thing as I did here, you will get your b1 t hat. Then you have your x2, and let's say it's regressed. So let me use the Greek letter theta for this one, that b2t. And then when you do OLS, so you're going to do OLS 3 times, 1 for y, 1 for x1, 1 for x2, assuming all of them have problems, y, x1, x2. Assuming all of them have trends, then you'll get b2t. So you get the residual from the regression of y on time, that's this. You get the residual from the regression of x sub 1 on time, that's this. And then you get the residual from the regression of x sub 2 on time, that's this. And then step 2 says, I was going for dramatic pause. Step 2 says that you regress your residual from y. So you have the regression now. Residual from y is going to be regressed on, not x1, but the residual of x1, which is b1t, and then the residual from x2. Sorry, I'm covering it. Okay, like that. So that will be n plus ub. So this is now your new regression model. That's step 2. So it is a regression not of the original variables, but of their residuals on each other. The residual of y regressed on the residual of x, and the residual of x1 and residual of x2. Okay? Now, let's see why. So that's the mechanical part of the detrending. So detrending means regress on time, get the residual, and substitute the residual for the original variable. But what's the logic behind that? Okay, let's return to this. The logic behind this is this. We write this as yt equals yt hat plus et hat. Okay, now what do you see there? What you see there is that the original variable y, the series y, can be decomposed into 2 parts. The y hat, the fitted value, and the residual. But that's nothing new. We knew that already. But what can you see here? Y hat, this part here, this part of the original series y, this part is this. And notice that this part here is a function of time. Right? And we say a linear function of time. So what you're saying, what we're doing when you are detrending, to detrend means to remove the trend, means I don't want that part of y that is a function of time. So I don't want this. Therefore, if I don't want that, then I'll just use that. See? Right? So the error curve is not systematically linked to y. To time. Not systematically linked to time. So Y hat is that part of Y that is not systematically linked to time. And therefore, you only use the other part that is not systematically linked to time. Okay? Questions? So that's method 2. You have method 1, just add a time variable in the regression. Method 2 is detrend all the variables and then do the regression using the residuals. So obviously, method 2 takes more work. So why would we ever choose it? We probably won't. Because they are equivalent. At least that's what I know of. I haven't seen any writing saying method 2 is superior to method 1. Method 2 obviously takes a lot more work than method 1. So, if it's simplicity we're after, then we just do method 1. However, the beauty about method 2, the beauty about method 2 is that you're actually seeing the process of removing the thread. So from a theoretical point of view, method 2 is probably more satisfactory because you are actually removing the thread. But from a practical point of view, method 1, which is just simply just adding a trend turn, is probably preferable. But discussing method 2 is not a waste of time because it's actually showing you what do you mean by removing the time thread. Okay, now, since we have just a few more weeks to go, I'm going to skip some slides. Those that are not important. So this is slide 22. If you want, take note of what I'm skipping. I'm going to skip 23. These are just side comments. I'm going to skip 24, still side comments. I'm going to go ahead and go to 25. Okay, slide 25. Okay, so I skip slide 23 and 24. Let me go to 25. All right. Just stop me at any point if you have any question. All right. Related to the problem of trends. So trends cause you problems. Related to that is the problem of seasonality. Okay? Seasonality. Okay, let's read together. So the problem of seasonality occurs when the data used is either quarterly or monthly. So think of your class projects. Are you doing monthly data? Are you doing quarterly data? For those of you doing the time series. Okay. So, as an example, say that you have data on sales. Sales of something. Now, it's traditionally higher in the fourth quarter. Everyone knows that. That sales are higher in the fourth quarter. As we say, they are the Burr months. October, November, December. Or, if you are using monthly data, then sales are higher in December because of the Christmas rush. Right? Okay. So therefore, season, if you have a regression where the dependent variable is sales, say you have a regression. Sales is a function of, I'll give you one. The sales of a company, say it's microeconomics. The sales of a company depends on, let's say, price of the product, let's say, advertising, expense, others. Now, but then, the sales of a company, if you're using monthly data or quarterly data, does not just depend on the price of the product or the advertising effort of the company. It also depends on the month. Doesn't it depend on the month? Or the quarter? So, just like a trend can create a spurious result, you also have to account for the season. What month is it? What quarter is it? Alright. Now, we have, again, two solutions to the problem of seasonality. So only appropriate for those people using monthly or quarterly data. I don't know about the more high frequency one, like daily. Season ko ba yung daily? I don't know. Okay, I haven't investigated that question, daily or weekly. But more for quarterly and monthly. Okay, method 1. Just like what we did with trends, we added time. So here, we're going to add something to the regression to account, to control for the month or quarter. So add the seasonal dummies to the regression. So in this case, let's say it's monthly. So Y is sales, X1 is price, X2 is advertising. And then once you're finished with the usual set of variables, then you add dummy variables for the month. And then, of course, following the principle of avoiding the what trap, the dummy variable trap, we exclude 1 month. Yeah? Could be any month, but just exclude one. So in this particular case, the excluded month is January. So it means every other month is compared to January. Okay? Alright, now you might be thinking, so that's a lot of lost degrees of freedom because we just added 11 explanatory variables. Well, yes, it is a lot of loss of degrees of freedom. However, if your data is monthly, you have to have lots of observations. No? So like, monthly data for 5 years is 5 times 12. So you have 60. So you can probably afford to lose 11 degrees of freedom. Because if it's monthly data, then you have more months. Okay. So it's exactly the same principle as the one of adding the time. So trend is more a problem for yearly data, while seasonality is a problem for monthly and quarterly. Okay. Then, the second, another example. Okay. So if you were using quarterly data, if your data is quarterly, let's say your Y is inflation. Suppose your Y is inflation. Inflation might display some seasonal effects. It might be higher in different quarters than in, just like sales. It might be higher in different quarters than others. Okay? We don't know. But, yeah. So, again, we include dummy variables for the quarter. And in this case, the excluded quarter is quarter number 1. Okay, let's see. If this is sales in September, okay, pop quiz. If this is sales in September, what is the value of this? 0 or 1?
0. 0.
Yeah, I'm counting where September is, right? Okay. So, if this is the sales in September, then this will take the value 0. This will take the value 1 because September is quarter number 3, and then this is 0. Okay? If it was March, this one will be
0. First quarter.
0, 0, 0. Okay, good. Okay, now let's read the second bullet point. In the case where no seasonality is present, then this can be verified by an F-test, such that delta 1, delta 2, etc. are 0. Okay, now, what this number 2 point is saying is that just because your data is monthly or quarterly, don't always jump to the conclusion that your variables have seasonal effects. No? Just because your variable or data is not yearly, but quarterly and monthly, still, you have to think about it. Is it prone to seasonal effects? There might be some variables that don't have any seasonal effect in them. Give me one. Think of one variable that is not affected by the month or the quarter, but you have data on it on a quarterly and monthly basis, but it's not affected by the quarter or the month. Tax. No, tax has season. We pay taxes in April. Okay. It has to be a variable that is pretty random, no? Which is kind of hard to think about because for most variables in economics, they do display this thing. Let's try. How about unemployment? Let's say we have quarterly unemployment figures. Is unemployment, do you think? I don't know the answer. I'm just throwing it out there. Does unemployment have any particular pattern? That if it's fourth quarter, it's higher or lower? We don't know. We don't know. Yeah. It's higher after graduation. Unemployment. Because you are unemployed. Yes. Oh, that's a good point, right? So second quarter after March, that's high unemployment. That's a very good idea. So there is a seasonality to unemployment, right? Okay. Anyway, so think of those things. It's really interesting. Okay. Now, note that the existence of seasonality does not preclude the existence of trends. Another interesting point. So just because your data is monthly or quarterly, and you say to yourself, oh, okay, so for my paper to show the teacher that I am listening, I'm going to adjust for the seasons. But it still doesn't exempt you from the trend. Whereas, if you are using yearly data, you are sort of exempt from the season. You just have to worry about the trend. But if you're using monthly or quarterly, you have to worry about two things: the season and the trend, because it does not preclude the existence of trends. Okay, so here it says, the value of sales in December may be upward as each year passes. So it's traditionally upward compared to other months. So sales in December is always higher than sales in February, sales in March, for most products. But what this is saying is that if you compare the many Decembers, December of 2010, December of 2011, December of 2012, December of 2013, etc., you might notice that it's still going up, comparing all the December months. So therefore, in this case, we can also add the trend. So which means to say, just because you have an equation like this doesn't mean it has to stop there. You can have Q2, Q3, Q4, then plus delta 4 times time. So you can also add plus a coefficient and then time to account for the effect of the yearly change. Okay. Now, in case the data you collected said it has already been seasonally adjusted, sometimes you get data where it says there, seasonally adjusted data. So let's say you get a World Bank data, or you get an International Monetary Fund data, and it says there it's been seasonally adjusted, then of course you don't need to do anything. But if you're that sort of person that is always suspicious, you might want to investigate how did they adjust it, what method did they use. So it will probably be found in the explanatory notes of the publication, in the footnotes. This is just really simple taking out the season. But see, this is an entire subject in itself. No? There are entire books written on just how to handle the seasonal effect. No? So, it's a lot more than this. There are alternative methods that we don't know of yet, or which we will never know, because this is introductory econometrics. No? But what I'm saying is that if the data says seasonally adjusted, it means basically you don't have to do anything, unless you're truly very skeptical person by nature, that you have to know what they did, and you sort of don't trust them. Okay. There are lots of Athenians like that, right? Okay, now, anyway, the second method of deseasonalizing, see, another term to add to your vocabulary. So, you detrend, you deseasonalize. Okay. So, a while ago for detrend, I said metaphor, debone a fish. I think this one is impossible to think of a metaphor in cooking. You season the dish, but you cannot unseason it. Alright. To deseasonalize. Okay. So deseasonalize the data before regression. Regress each of the y and the explanatory variables, okay, those factors or variables where there are the seasonal effects, on a constant in the seasonal dummies. Then obtain the residuals from these regressions. It's just like the method 2 of trends. Again, you will replace the original variable by the residual. So instead of regressing with respect to time, you regress on the seasonal dummies. Same principle. Then step 2, regress the residual of y and the residuals of the explanatory variables. Okay, no further comment needed. Okay, that for that. Let's go to the next chapter. Okay. We are now in chapter 11. Chapter 11. So we'll try to get as much in as possible. Okay. I am very optimistic that we will get a lot of things in, if I skip some inessential things. Okay. Chapter 11 is the second chapter discussing time series. And then after that it stops. And in chapter 12, hindi pa pala, dami pa pala. Chapter 11 is the second chapter in time series. And then there's a third one, which is also incumbent upon us to discuss, serial correlation. So expect me to send that to you soon, to Paulo. Okay. The title, I don't like. The title says, Further Issues Using OLS for Time Series. It gives the impression, when you say further issues, it gives the impression that, oh, it's additional material that is not central. But actually, when you look at it, it's important. It's not just further issues. So I don't know why Woolridge called it further issues. So have you read this ahead? Okay. I had to ask. Now, the first slide defines what we mean by a strictly stationary stochastic process. Okay. So listen closely. In time series analysis, the concept of stationarity is paramount. Because whether the variables you are using are stationary or non-stationary will have repercussions on whether you can use OLS or some other method. So we have to discuss what do you mean when a stochastic process is stationary. Now, again, review. Stochastic process is a sequence of random variables indexed by time. Okay. Now, you will find this definition at first extremely challenging, or maybe not. Maybe not. challenging, not extremely. No? But the key is to try to visualize it, I guess. But again. So we have here the concept of a strictly stationary stochastic process. Okay, so our stochastic process is a sequence of random variables indexed by time. Okay, so let's say x1, x2, x3, x4, x5, x6, etc. Actually, the simplest stochastic process is just tossing a coin repeatedly. If I toss a coin now, I don't know if it lands heads or tails. That's a random variable. Then I do it again, second time, x2. Toss a coin, heads or tails. Third time, heads or tails. Or toss a die. Except that there are 6 possibilities. Okay. So a stochastic process is a sequence of random variables. Now, each one of these, just to refresh our memories, possesses a distribution. Each one of these possesses a distribution. So for example, if x1 turned out to be 4, the value of x1 turned out to be 4, it came from a distribution where, say, the mean of x1 is, say, equal to 5. And what actually happened in history is 4. Okay? For x2, it comes from another distribution, possibly not like the one before it, possibly right-tailed or positively skewed. Now, let's say the mean here, the mean of x2 is equal to 2. And then what came out was let's say 5. Let's say this is 5. So it came out that the actual result is so much higher than what was expected. Okay? So each one has a distribution. This one here will also have another distribution, and so on. Okay, now let's read the definition. You say that the stochastic process is strictly stationary if for every collection of time indices, the joint distribution of x sub t sub 1, x sub t sub 2, all the way to x sub t sub n is the same as the joint distribution of x sub t sub 1 plus h. I love saying it. X sub t plus 2, x sub t sub 2 plus h, etc. For all integers h greater than or equal to 1. Yeah, that's the definition. Okay, now what does that mean? Yeah? So first we have to understand, what do you mean by for every collection of time indices? It means that, okay, I have here my different random variables for each time period. I can pick any random subset. For example, I can pick, say, 2, 3, and 4. So my collection of time indices, my collection is 2, 3, and 4. I can pick, say, 5 and 6. No? Alright? It says every collection. Doesn't say how many, and doesn't even say consecutive. So it can also be, say, 1 and 3 and 5. Alright? So I can have x2, x3, x4. I can have x5, x6. I can have x1, x3, x5, and so on. Okay? Now, so for every collection of time indices, then you have a joint distribution. Okay, let's now tackle this. So say I selected my x's. So I selected my x's. Then you talk about a joint distribution. Alright, let's talk about that. And here is where your prior statistical training will pay off. When you say distribution, I know you know this. If you're talking about only one random variable, like say x2, and let's say this is the probability distribution of x sub 2. It means for all the possible values of x sub 2, no, this one here has the greatest chance of occurring. Whereas these ones here at the tails have the lowest or lower, comparatively lower chances of happening. Let's say number of children is a random variable. Let's say. The greatest chance is that a person of fertile age might have, say, 3 children. But it would be less usual that he will have, let's say, just 1 or say 7. Okay. Now, when you say joint distribution, what do you mean by joint distribution? Now, it's easy to imagine for, let's say, 2 variables, let's say x5 and x6. If it's x5 and x6, the joint distribution will be 3-dimensional, right? So you have x sub 5 and x sub 6. Now, x sub 5 can take on this value here. X sub 6 can take on, say, that value. No. And of course, it's hard to draw the hill, but then, no. Okay? Then therefore, this will be a certain value here. Okay? Right? So, what is this value here? That's the probability. So this is the vertical axis is probability. This one here is the probability that x6 takes on that value, while x5 takes that value. Okay? Now, so reading the definition again, it says there, we have strictly stationary stochastic process if for every collection of time indices, the joint distribution will be the same as the joint distribution of the original subset you chose compared to this, which is shifted h periods into the future. So for example, if I have h, let's say if I have h equal to 3, it says that h can be any value between 1 and then all the way, starting from 1 upwards. If h is 3, then I'm talking about, what am I talking about? Let's say, relating to this one, I'm going to have x8 and x9, right? So this one here is just shifted by a certain amount. So instead of x5, shifted in time, not shifted geographically, shifted in time, displaced in location in time. Okay, isn't that wonderful? All right, now. Okay, so it means that this one will also have the same distribution as that one. Alright? So same shape, same parameters, etc. So this one is just this, shifted 3 periods forward. Alright? So yeah. So now, my example here is for x1 and x2. Now, since x1 and x2 are separated, are adjacent, one next to each other. So will be x sub t and x sub t plus 1. Okay. So, yeah, so you understand the meaning of strict stationarity. Now, why did we invest time to learn it? Because if your data is strictly stationary, one of the payoffs there is that go ahead, you can use OLS, which we will later on find out. So if it's strictly stationary, no problem. But then the thing is, what do you observe? The condition of strict stationarity is very strict. Okay. Again, I don't want to define the thing by its very name. It's very strict. What kind of data follows this? We don't know. Will we ever know? How do you know it? How will you test it? You can never know. We can never know. Why? Well, first of all, think about it. It says every collection, which means to say you have to try every combination. And how many are they? So many. So many combinations. And then for each of the combinations, you have to verify, find out whether the shape of the distribution is preserved for every h. No? Plus 2, plus 3, plus 4, plus 5, plus 6. That's why, don't go, the bell is ringing. That's why we have the weak stationary. Because the strong stationary is too strong. Alright, so, anyway, let me check attendance.